Good morning, students. Now we have started magnetic circuit, magnetic material, and now in last two lectures we have seen introduction of the magnetic materials. What are the magnetic materials? Which materials are magnetic materials? We have seen few definitions. So if you could remember that we have just seen magnetic materials, permeability, susceptibility. We have seen difference between permeability and susceptibility. So video lectures are available. You can go through that. We have also seen what is mean by magnetic dipole. I told you di means two and pole means poles, south pole and north pole. So when two poles are displaced with some distance, they will constitute magnetic dipole moments. We have also seen orbital magnetic dipole moments. Okay, so let us now see in detail orbital magnetic dipole moment and magnetization, because we have seen a relationship between permeability and the susceptibility, and at that time I have told you that other things I will just take in the next lecture. So what is the relationship between permeability and the susceptibility? We have seen what is mu r. Mu r is the relative permeability, and mu is equal to b upon h. This you know, mu is equal to b upon h. Like susceptibility is also equal to m upon h. In susceptibility it is not this magnetic flux density, but it is the magnetization. So you just write down these two formulas. Mu is equal to b upon h and xm is equal to m upon h, and we have seen the derivation of this. And what is the susceptibility? So permeability is equal to 1 plus susceptibility. Okay, so susceptibility will be equal to mu r minus 1, and susceptibility can be negative. Permeability cannot be negative, but susceptibility is negative. So that definitions we have seen. Orbital magnetic dipole moment, I have told you what is dipole moment. When south and north pole, two poles are displaced by some distance, they will constitute dipole moment. I have shown you the video also. And orbital magnetic dipole moments means here electrons are moving, and whenever electrons are moving, it constitutes current, because whenever electrons move, current is there, and when current is flowed or passed through the wire or conductor, it produces magnetic flux. You know, current carrying conductor, when it is placed, it produces two flux, means magnetic field it produces. So when electrons move in the orbit, it is nothing but electronic current, and as it is the current, it will also produce magnetic flux. And whatever is the two dipole moments will be constituted, that will be called as orbital magnetic dipole moment. And that also we have seen electric current is EF, and magnetic dipole moment is 1 half E omega 0 R square. So this is omega 0. So that we have seen in the last session, because when you will see electric current due to the electron is EF. So for this frequency you put angular frequency omega 0 upon twice pi. So when you will put F is equal to omega 0 upon twice pi, then what will be electric current? E into omega 0 upon twice pi. So that will be the current with angular frequency. Okay. So that we have seen in last session. So magnetic dipole moment will be equal to current into area, because dipole moment we have seen the definition of dipole moment is current into area, and for circular current, area of circle will be pi r square. So that current is EF and area is pi r square, so that will be EF pi r square, but you put F is equal to omega 0 upon twice pi, so you will get the dipole moment is equal to 1 half E omega 0 r square. This also you remember as a equation for solving simple problem. So magnetic dipole moment is 1 half E omega 0 R square. Okay. So up to this we have seen. Now magnetization we will see, because I told you I will not take formula in one session. We'll see in next session. So this formula we'll see what is magnetization in terms of susceptibility. Okay. So magnetization, all materials are affected by presence of magnetic field. We have seen all materials are magnetic. Even wood is magnetic. Water is also magnetic. Only non-magnetic material is vacuum. True means non-magnetic material is vacuum, because in vacuum no means particles are there, atoms are there. So vacuum is a good non-magnetic material. So the magnetization of dipole moment per unit volume is called magnetization. So when dipole moment per unit volume, you can see number of dipole moment per unit volume. Just correct it. Instead of this, you can just say number of dipole moments per unit volume is magnetization. Now, earlier in unit, we have seen polarization, and polarization and magnetization are analogous term. So everything is same. Dipole moment, electric dipole moment. Here magnetic dipole moment. There is polarization. Here is magnetization. So formulas will be also same. Definitions will be also same, and only word you have to replace. Here magnetic dipole moment per unit volume will be magnetization. There electric dipole moment per unit volume will be polarization. Okay. So this is described by M. Magnetization is described by M and polarization is described by P, and unit is ampere per meter. Okay. So when magnetic field is applied to material, magnetic induction means flux density is the sum of the effect of vacuum on the and that material. I told you, suppose now you will just see flux density. Total flux density will be mu 0 h, where mu 0 is the permeability of free space. So what is the flux density produced in the free space? And when you will replace that free space by putting some material in that free space, then you will observe that flux density is enhanced. So why flux density is enhanced? That flux density is enhanced due to the production of the flux density due to that material. So B will be equal to mu 0 H plus mu 0 M. This will be due to the free space and this will be due to that magnetic material. Okay. So B, total B will be equal to mu 0 H plus mu 0 M. And you know that B is equal to mu 0 mu R H, because whenever we use material, we have to use relative permeability. This is for free space. But what is the flux density in any material? That will be equal to mu 0 mu R H. This also you know. So put this B mu 0 mu R H here. So you can get this equation mu 0 mu R H here will be equal to mu 0 H plus mu 0 M. So you will get this equation. Okay. So now you can just see here H term and H term. You bring both H term at one side. So what will be mu 0 M? Mu 0, because we want to see what is this magnetization. So mu 0 M will be equal to both this H term will be at right hand side. So it will be mu 0 mu R H minus mu 0 H, right? So now what will be that? So here H you can take common. Mu 0 is also common. So take mu 0 H common from right hand side and it will be mu R minus 1. Okay. So what will be magnetization M? Magnetization M will be this mu 0 will come here. So it will get cancelled. So M will be equal to H into mu R minus 1. So M is equal to mu R minus 1 into H. And in last session, we have seen mu R minus 1 is susceptibility. So you can just write down this M is equal to susceptibility into H. So remember this formula for solving problems. So that is about the magnetic susceptibility, and we have seen the difference between permeability and the susceptibility. So magnetization M of material can be expressed as number of dipole moments. These are dipole moments P suffix M, small p, total P, not that you can just say U, mu also you can use symbol for the dipole moment. So it will be small p. So magnetization M will be equal to number of dipole moment into dipole moment. So where N is the number of magnetic dipoles per unit volume. And magnetic susceptibility, we have seen magnetic susceptibility is mu R minus 1. That is a formula, but it is a magnetization per unit magnetic field intensity. Okay, and it is the liability of the material to get magnetized. And mu R is ability. So I have told you the difference. Now it is a dimensionless quantity because magnetization and field intensity have same unit and therefore it has become dimensionless. All materials are classified by sign and magnitude of their susceptibility. Relative permeability is only having magnitude, not the sign, but susceptibility is having positive or negative sign. Okay, so this YouTube I have shown you magnetic dipole moment. So that I have already told you. Now I just want to show you electric dipole moment and the torque. This is the visualization. So if you could visualize this electric dipole moment. Same you can just visualize for magnetic dipole moment also, because this video I could found it very easy, very nice and easy to visualize it. What is mean by orbital dipole moment? So that is about electric dipole moment. Same is for magnetic dipole moment. So that will be revision of both electric dipole moment and magnetic dipole moment orbital. So let us watch that video. Okay.